Hello, good evening everyone. I hope I am audible and the screen is also visible. Can anyone just confirm?
Yeah.
Yeah. So good evening. So this session is about the main objective of the session is essentially to help you in solving some of the assignment problems, and also we'll be discussing some of the other problems with respect to the previous week's lectures. So this week we will be discussing on week 1 lectures, which primarily discusses on some of the basically recap of whatever you have learned in conservation of mass, momentum and energy, and also it also deals with the Navier-Stokes equation. So we'll wait for a couple of minutes if anyone of the joins, and then we'll get started. All these sessions will be recorded and all the material will be shared to you accordingly in your NPTEL. You will find at the bottom indicating you will be given a Google Drive link where you can access all the material, and at the same time the records will be uploaded in a YouTube channel, the link of which will also be shared with you once the session is completed. If you have any other doubts that you need to discuss in the session, that we can have the discussion, and if suppose time doesn't permit, we can have it in the next week, or you can post the questions in the discussion form of the NPTEL. We'll try to address in that particular forum itself. I guess we can get started. So we'll directly start solving some of the questions. So in the class, if you would have gone through the lectures, you would have seen that the first the professor starts discussing about something called continuum hypothesis. So the entire course is based on this fundamental hypothesis that we are dealing in the design where this hypothesis is valid. So can any one of you briefly unmute yourself and describe what this hypothesis is, or maybe try to answer this particular question. Here I have shown 3 different images. So case A, B and C. So in each different case we will be taking 3 different length scales. So which one of these do you think satisfies the continuum hypothesis?
Well, I briefly remember that the length scale is less than some nanometers or something, then it is
Okay.
not considered as continuum. But here I don't see any dimension on the x-axis and y-axis, so I'm not sure what exactly.
Okay. So
But I'm taking a brief case. Maybe C looks like, because you have the square blocks and you're trying to approximate each those blocks with some x number of points. Yeah, it's not much clear for me, the question. The question is not much clear for me. I wanted to.
yeah, let me just repeat the question. So the one you are saying is length scale, if it is on the order less than some mm or so, you are saying the continuum hypothesis is not valid. So our length scale should be chosen in such a way that it is greater than in a millimeter range. So what should be the basis that you say millimeter is the length scale that you have chosen? So the fundamental thing that you have to consider over here is essentially the number of particles. So here I did not mention the length scale as millimeter or something, just consider it as some unit. So if you consider this this particular image, I have divided it into 4 quadrants. So this is my entire domain that I need to study about. What I do, say for suppose you have some property like density. Density is essentially your mass per unit volume, but there are different ways in which you can consider your volume. So you can consider case A, where you can treat the entire thing as volume, and then you just calculate the total number of particles and then divide by that volume. Or in this particular case, you can just count the particle density, basically number of points per unit surface area. So you will be getting some value in case A. Now if you go to Now if you see in part B, when we divide that particular area into 4 equal parts, then each particular block will have a different number of different particle density. Say the quadrant 1, quadrant 2 might have a value different from quadrant 3 or 4. So what is that we are trying to say when we mean the length scale should be greater than mm is essentially, that becomes clear when you see in part C. If you see in part C, if you see this particular quadrant, if you see in this particular quadrant, you see there is only one particle over here, but in this particular quadrant there are so many particles. So if you move across different spaces, you will be having different values of densities. So only if the scale you have chosen is sufficiently larger is when you see all the values across different quadrants or different sections around which you are taking average will be equal, and then you will call that particular region to be valid for continuum hypothesis. So that is how do we define it? Essentially is from the concept of Knudsen number. So we define a non-dimensional number with respect to the mean free path of the particles and with respect to your characteristic length scale, where this lambda is your and L is your characteristic length. What do I mean by mean free path is essentially is a distance traversed by the particle between two successive collisions. So you might have read about the kinetic theory of gases, where we define this mean free path. You define your gas is composed of several particles, and each particle will continuously move. So the time so one particle can move the distance between, there are so many particles, so that essentially the distance between these two particles is what you are calling mean free path, and your length scale should be chosen such that it is much greater than this mean distance. Only in that particular case you can consider that continuum hypothesis valid. So essentially your Knudsen number should be less than 0.01 for your continuum hypothesis to be valid. So when you are considering gases, you have a very much larger mean free path. So essentially your length scale should be sufficiently larger to compensate for that, and that is why you have in the order of millimeters. Now when you go to from gases, if you want to go to some solids or liquids, where you essentially do not have that much mean free path, when you consider just a solid where just particles move about their mean positions, the mean free path will be very less. So in that particular case your length scale can be even finer, so you can go less than millimeter, you can go up to nanometers or micrometers, and even then your continuum hypothesis will be valid. So coming back to the question, the essential idea is the scale you have chosen should give you some uniformity within your entire domain. That is happening in case of in A you cannot say anything, but when you go to B, you can see that each quadrant will have more or less similar number of particles, and then your hypothesis is valid. But as you go into even finer length scales, you can see that some of the particles are getting isolated, and it so happens that it can happen that there can be regions where you do not have particles at all, and then your definition of density goes to 0 in some particular regions, then a continuum hypothesis won't be valid. So why are we bothering about this continuity and all of that is essentially because we are trying to model our fluid using differential equations, and all those equations are valid only when you have continuous functions. The function need to be continuous throughout. In this particular case, if you consider here you have around 3 particles and you have only 1 particle, and then and the function cannot be continuous in this particular domain across this boundary. So we should be taking a length scale much larger than this. So let's go to question number 2. So essentially here I hope 1 is clear. Now for the second question, again we are discussing about 2 different kinds of approaches to describe fluid particle. One is the Lagrangian approach, the other one is the Eulerian approach. So the fundamental difference is in the Lagrange approach, you consider each particle and try to follow it across its entire, like you try to track the particle continuously. But in Eulerian approach, you fix your entire domain, you fix your domain, and then you give a flow field and then try to see whenever a particle comes into that, it follows the flow field dictated by it. So, and then we have how to relate the Eulerian and the Lagrangian. We have one conversion from the material derivative with respect to this. So this particular problem tries to address that. So if you see, there are three particles, and the particle it's a 2D flow, and then you have the x coordinates given by where this small t is your time. So x is x equal to t and y1 equal to t square, and the second particle is following the approach x2 equal to t and y2 equal to 1 plus t square. So similarly, there is a third particle that also has some profile given to it. So we try to calculate acceleration for these particles, and then we will try to see out of these following velocity fields, which of these fields will try to represent the same flow field as dictated by the Lagrangian approach. I hope the question is clear.
Yeah, it is.
Yeah. So maybe I will wait for a couple of minutes for you to solve, and then I will start discussing. Just to recollect, so from the Lagrangian form, Lagrangian to Eulerian, you have the relation. Say if phi is one of the property, or it can be any coordinate, then the material derivative is given by
So, I mean, it's kind of funny. So, I've taken material like this P1, P2, P3 are essentially you're tracking like you have this kind of ball and it's just to time derivative, total time derivative.
yes. So
For
you
all
just
the
get the
three
velocities.
particles being 1, 2 t, and the only expression I can see in ABC is A. So that's how I solved it. I think this is the right view.
Yeah.
Yeah.
So you are essentially saying. So the three particles will be moving in three. It's a kind of a laminar flow path where you have three different paths. So all of three will be moving in this particular way. So you do the time derivative and you get that. So the thing you have to essentially check is the second part where the accelerations will be same or not for all these flow fields. So have you tried checking with the part A and B? Like both of these should give you the same values, right? Or is it only A?
Only A.
Okay, so if you try to substitute in this expression,
flow field is essentially
yeah,
it doesn't depend on place. It depends on the time, and each time at every position you have same velocity. That's what for these.
Okay, so this is the expression you are having, right?
A. I mean, I got A. I could be wrong.
No, you got A. So essentially, you substituted this into this, and you will get from this you get a u equal to 1 and v equal to 2t. So you are essentially substituting that back here, and you get option A. So what I am trying to ask is, you have this particular formula that is derived in the class, right? How you derive your material derivative with, like, this is your Lagrange form and this is your Eulerian form. The RHS is your Eulerian form. So try to substitute part B also, like the second option as well, into this one, and try to see if it matches with this. In terms of acceleration, I am trying to ask, the question is basically, do you get the same acceleration? Not the velocities. So if these are your velocity components, then you have ax equal to 0 and ay equal to 2. So the first flow field will give you ax equal to dou u dou t plus u del u del x plus v del u del y, and similarly ay is given by so from this, if you substitute option 1, you can directly get that u is essentially 1 and v is 2t. Sure, ax will become 0 and ay will give you value of 2. But if you see the second option, your ax will essentially be del u del t is 0 and your all other components will be 0, so ax is 0. You try to calculate ay, even your del v del t is 0, but essentially you have the second component where del v del x is some finite quantity, so you will still get the same value of 2. So like you can get the same acceleration values even though your velocity fields might be different. Like essentially what is happening here is your x which you are considering here is again a function of time, where x of t is equal to t, that is the particle motion that is being traced, right? So both option A and B will satisfy that. I hope it is clear. So A and B are essentially identical. Now if you try to substitute for C and try to get the accelerations, can you try that one as well?
There's a lot of
Actually, okay, if you try to see for the third part
I
as
just want to ask. I just want to ask something. So can you discuss like this, or is it only one way? Because how is this actually organized? So that others don't get this. That's what I want to ask.
the session is essentially meant to help you in solving your problems.
This is fine, right? Like discuss and solve.
Yeah, it's about 2 hours session. So if you would have already come prepared for with some questions, then it will be more effective. Otherwise,
Yeah,
I
so
have
want
some.
you. Yeah, I just wanted to lead. If you're going out of time, you just keep as in go fast.
Yeah, sure. I prepared for a set of like I was supposed to discuss around 10 questions. So if you have any other doubts, maybe that will go. Then we will see accordingly, and we can have this discussion at the end after completing all the problems. So as of now, it's fine. So I think this question is clear. We can go to the next question. So here we are giving you the scalar field. So there is a 2D unsteady flow where the density field is given by x times t, and your x component of velocity is given as minus x by t. The questions are essentially, the first one is to determine the y component of the velocity such that the flow satisfies conservation of mass. In the second part, I am asking you to calculate the divergence of the velocity field and see whether the flow is compressible or not. And the third part is essentially something which we should start first. So as you must have gone through the lecture where the professor mentions that when your del dot u equal to 0 is essentially what you are calling the flow as incompressible. So in that particular case, your density is a constant, and hence that is why the name that we are calling it as incompressible. So in this particular question, I am telling you that rho is a function of both space and time, and that equal to x times t. So do you think this flow can be incompressible, or how do you approach it?
No, it's not incompressible because we have t, right?
Yeah, you have x and t, both are there. It's both a function of space and time.
No, I mean, when we take divergence,
Yes.
it remains, so it's not 0. It's not incompressible.
Yeah, so did you calculate the divergence? So I've given you the x component velocity. So for you to calculate the divergence, you need to calculate the y component as well.
V,
Yeah, so the first step is essentially to calculate the y component of velocity. So the starting step would be essentially start with writing the conservation of mass. So I am giving you rho of x by t as x times t, and u of x comma y comma t as minus x by t. First question is to determine v of x y by t. So first, when we write the conservation of mass, essentially your continuity before your continuity equation. Or maybe I can write in the expanded form.
So we got xy plus
you got v as xy plus c.
c. Yeah.
Okay, say suppose the initial velocity, like at 0 comma 0, the chat is 0 velocity, so you are saying essentially v as xy. So
I got it, but I want you to solve it. So let's see.
okay. So basically this is how you start with. This is your conservation of mass. Dou rho dou t is essentially your x plus so since x and t are independent of y, so essentially get del v del y equals 1 by t, which gives you y v equal to y by t. So you can just check if something is wrong. So
Yeah.
so this is your y component of velocity. So the next step is essentially to calculate your del dot y, divergence of velocity, del dot u bar is essentially del u del x plus del v del y. So if you happen to see here, this just turns out to be del u del x is minus 1 by t and del v del y is 1 by t. So this is essentially 0, which means the flow is incompressible. So what do you think is happening here? Like your rho, as you're seeing it, is both a function of space and time, but then your divergence of your velocity field is coming up to be 0. So do you think the flow is incompressible or not? Or any comments or anything? Or did we miss anything? Did we do something wrong?
So I think he's more considering at each instant, but density is changing.
So how are you confident that density is changing?
This is function of x and t, right?
So let's come back to the original one. So when we started out, even in the previous question, x is essentially a function of time again, right? So the one I have written is it in an explicit form, but if you see, rho is essentially x times t, where your x itself can be a function of t, right? So like even if you yeah,
we're taking a Eulerian field, right? That's the problem. It's actually Eulerian conservation.
yes,
So whatever you put,
yes.
you are taking, like, say you take x and y.
Hmm.
You have density functions varying throughout x.
Yes.
And if you remove t, just say rho is equal to x. So with x changing, rho will change.
Yes.
Right. And since there's also t, so there's something like more radiation, time and with x.
Yeah, but x cannot change arbitrarily. X is again dependent on t. So since both Eulerian and Lagrangian should be consistent with each other, x cannot be changing independently of time, right? So like if you start with your original derivation, you're saying something. Yeah, continue.
I understood. I think what we're trying to do is we take a parcel at some time and at some point x.
Yes.
And we're trying to track it. It goes to some other point. That's what material derivatives do.
Yes.
And the way density is changing with time and x position and velocity, whatever we have, such that the parcel moves, it is moving such that the parcel is incompressible. Essentially, that's what we're trying to see.
Yes.
Even though the density
Even though the density is a function of space and time, eventually if you try to make it in the completely fully function of time, then it will be independent of time. That's what we'll be proving now. So how
it's
do you
clear, right? What
yeah
is correct.
so essentially how do you get that this particular term x times t is essentially constant? So if you recollect, we have essentially u equal to dx by dt, where I have given u as minus x by t. So if you just substitute this particular value here, you get dx by x plus dt by t equal to 0. So this boils down to x times t equal to constant. So essentially this is your density. So rho is essentially a constant. Because of the flow field, the x cannot be changed arbitrarily, it is constrained in this particular way, so your rho will always remain constant, and that is similar to the expression you got over here, del dot u equal to 0. So like either this or this are essentially the same. You can try to prove it also. So the conservation equation you have is,
So what you are trying to say is at any given time t,
yes,
there is this contour of x or there is some line which parcel has to move, and that line the density is constant.
yes,
So,
yes,
but this is a bit strange, not strange exactly, that's not right word to do. So when we take this material derivative and we're equating it to 0, I mean, conservation of mass, it states that
sorry. Can you come again? So you are saying we are, I didn't get that thing you are asking. So material derivative is essentially we are making, so you are essentially saying d rho by dt is 0?
We are trying to enforce this condition. Enforce as in this conservation of mass, not enforce. Trying to find the density field or velocity field such that it's satisfied.
Yes.
Okay, so I'm just thinking this in terms of incompressibility.
So this isn't what conservation of mass says, right? D rho by dt is equal to.
What I'm asking is, do you think can we have a density field?
Yes.
Is changing, which is not, which is compressible. Still we can have this. So yeah, I'm just saying that. So there is this partial say.
Okay, so you are saying del dot u can be 0 and still you can have varying density field. That's what you are asking?
Not del dot u. Because if you have del dot u equal to 0, you can't have density field. It has to be constant.
Okay.
He's saying since we have come through this material derivative kind of thing, so can I have, if you take d rho, capital D rho by dt equal to 0,
this particular expression.
Can we have a density? Of course, I mean not of course. I'm asking if can we have a density field such that it is not incompressible.
So
because
okay, let's get back to that. So you are essentially like this particular equation is always true. So you agree with this, right? This is conservation of mass. So these are your source terms and these are your flux terms. So essentially the net should be 0. So if I just expand it, what do I get? So what is this expression? Del dot rho u can be written as u dot del rho plus rho times del dot u, right? So this is your material derivative component, d rho dt. So if you are essentially having this particular quantity to be 0, then you will eventually land up in a situation where your del dot u will go to 0, and then your density will again depend on like your x component will again be constrained by the time. So like you cannot have such density field in the first place. So like this is what your incompressibility says. Like if this this particular second component, like either one of these terms is 0, the other term goes to 0, right? So
I mean, no, that's right. Also, we can have the second term to be some plus quantity, the left term to be some negative quantity.
Yeah.
So it is incompressible.
Oh, sorry. Right? That will be compressible. If one of these terms is non-zero, then it will be non-compressible. Sorry, it will be compressible.
Yeah, I mean, it's clear for me now. whatever
Yeah.
question I ask.
Okay.
Next question.
Okay, this is a general question. So, when you derive the conservation of momentum, so you have several terms on your LHS. So, essentially, you have surface forces and body forces. So, which one of these do you think are part of surface, and which of these are part of body forces? So, before going to that, essentially, how do you differentiate between a surface force and a body force?
Whatever which is force which is comprised of volume, as you increase the volume,
Hmm.
it is
So,
called body force.
okay. So, which of these
And whatever,
options?
I think weight is Nagaraju wants to answer.
Sorry.
Yeah, in fact, body forces means, the complete force which is act upon the body, complete body, in fact, like gravitation and centrifugal force, electromagnetic force, and this kind of force which are acted on complete body. That's the body forces, I think.
Okay.
Can you
So,
answer,
In,
Nagaraju? Can you answer? Maybe given these options.
I guess, electric field, the fluid particle is charged, I think.
okay. So,
A and B are body forces, and C and D are surface. That's what I'm sure.
so this you are saying is a body force. This you are saying is a surface force, and
No, no.
then
A is body force as well. A is body force.
A is body force. Okay.
B is also body force.
Okay. And these two are
C and
surface
D are
forces. So, though it is not mentioned here, what do you think hydrostatic force will be? Like, because of hydrostatic pressure, there will be some force, right? So, what do you think that force will be? Will it be a body force or a surface force? So, like, hydrostatic pressure is essentially because of self weight of the fluid, right?
uh,
So, what do you think it is? Like, will it be body force, surface force, or I do not have to consider or anything like that? Any comments?
I think surface force.
It's a surface force.
Pressure. Pressure is essentially science on surface. P is not P times the force acting on pressure. It actually has additional normal component. You see the direction.
So,
Yeah.
if this is my fluid element, and so you're essentially saying it only acts on the surface.
So if you see, so you have pressure is a kind of scalar, not kind of pressure is scalar quantity. And when you convert it into, you want to compute the force acting on the body because of pressure, then you have to have a surface and a normal. Else you can't define pressure as, like else you can't convert pressure. No, you can't
So,
describe or
essentially, you need one surface, enclosing surface. Only then you will be able to define your pressure, and it won't be acting inside the volume. So, hydrostatic pressure is a surface force. Now, the part A is essentially the weight of the fluid on top of the element I am considering. So, if this is my fluid particle, question A asks is a force because of the weight of fluid on top of the particle. So, this will be only acting on the surface of the element. It wouldn't be acting on the volume of the element, right? It wouldn't
Yes.
vary even if the volume changes. So,
Yes.
this essentially is a surface force. Now, when it comes to the second question, where you have charged fluid and then it is placed in an electric field, that because of the electric field, the entire fluid experience forces inside the volume. So, that is how you named it as a body force. Now, let's come to both part C and D. So, since in your, like, even you might be aware in your solid mechanics or in rigid body mechanics, these action reaction forces will always act in pairs, and overall the net, in absence of any external forces, the net internal forces will cancel each other and overall effect will be zero, right? So, if you just consider the intermolecular forces between these particles, whatever particle I am considering here, both these forces will cancel each other. The only things that are of significant are essentially between the particle inside the fluid element and outside the fluid element, right? Those are the only forces that contribute to the net, and those are the ones that act only on the surface of the fluid element, and they won't be essentially contributing to anything inside the fluid, right?
Yeah.
So, these things would be considered as surface forces. So, but uh, so what do you think surface tension will be? Will it be a body or a surface?
So surface.
Okay, just as the name says, it's surface.
So that you can name it anything to anything.
Yeah.
You can name anything to anything. you have the expression. I think C is gradient of curvature. You don't have a volume. So that is the expression for definition. This answer like that.
Okay. Okay, this is just to derive this thing. This thing is already been discussed in the lecture video as well. So if you start with this particular expression, material derivative of rho times phi, where phi is some scalar quantity, is a some scalar field, then you have to prove that this particular relation holds. Maybe I'll wait for a couple of minutes. You can try to derive this one, or maybe I'll. It's just applying the chain rule. And this equation will be used a lot throughout the course, so it might be helpful if you just do it once. You can split this in several, like you can apply chain rule in multiple ways. Which of these ways do you think I can apply it for? I can either bring the density out, or I can bring the scalar field phi out. Maybe I'll try doing the phi first. I hope you are all like okay with this vector calculus, like applying chain rules using divergence and all of that. So if you apply chain rule considering phi as your constant quantity, you bring it out, and this is what you get with. And then you just group terms with rho and phi separately, so you'll be ending up with rho times del phi del t plus like the first term and this particular term u dot del phi, and if you group the terms with phi together, you get del rho del t plus del dot rho u. So this particular term over here is essentially your conservation of mass, so this goes to 0, and the first term is essentially your d phi dt, like it's a material derivative, right? So here phi is any scalar field. So say suppose if I put phi as the x component of velocity u, so what will be your left hand side if phi is the x component of velocity? It's rho times acceleration, so it's essentially force per unit volume along x direction. Similarly, along the y component and z component, you get all the forces, and that's how you derive your conservation of momentum. And then in this question, essentially deals with the calculating the power, net work rate, or essentially your power on your system. So, you know, like from rigid body, we already know that power is given by F dot U, and you already have the expression for F. So you can try solving this, or maybe you can start with say you have a 2D element for a simple case. I hope everyone is conversant with the tensor notation, or maybe I should give a brief of what a tensor notation is. So the notation here is like if I write something like dou ui by dou xi, this is essentially a divergence of u. So the index ui essentially means a vector ui cap plus ui j cap plus uz k cap. So by ui is essentially a vector, and when I is essentially your index will run from 1 to 3, And in a tensor notation, so if I say del ui by del xi, if there is a repetition of indices, it means you have to do the summation for all of them. So this gives you del ux by del x. And similarly, when you have two indices, then you have to do all the combinations. So like when you have tau I say, that is your shear stress, that essentially gives you a 3 by 3 matrix where I and j run from 1 to 3. I hope. And similarly, you fill all the values, so you get the shear stress answer. So I think the derivation is already done in the lecture video, where you will consider the fluid coming in. You have certain force times volume, so it says suppose you have P times the area is the differential element. So if I give an axis as xy, this as z, consider just the 2D case. So you will be having P times u acting towards this side, and on the other side you will be having P times u plus if the origin is somewhere around here. So the net work will essentially be the difference of these two. That will give you the quantity we are defining is per unit volume, so you essentially get minus del x of pu. So that is just for the case of static pressure. Now similarly you will have for the shear stress also. Maybe I'll wait for a couple of minutes so you can try and solve it yourself. If you face some difficulties, maybe then I'll just show how it's done.
So it's like we have, so the pressure force is gradient of P by rho, of mu rho. You have to take the dot product with Q, right? So
You get the power.
power, right? So
Yeah.
first
So this is that first pressure term. The second term is essentially with respect to your shear stress. The sign change is essentially because your pressure, the pressure P which we are considering is essentially hydrostatic, that is always compressive in nature. So there is a minus sign over here. Well, the shear stress is a kind of a tensile one, so you have a plus sign over there. That's the only difference. And in this particular derivation, like we have assumed that there are no body forces. Say suppose you have some body force, then you will be having some additional terms that essentially will be like plus,
dot U,
sorry, plus,
G dot
yeah,
G dot G
yeah,
dot
G
GI
dot GI dot UI. So that will be your body force term. If you have any other terms, that will be added from in this one. So we'll go to the next question. So I hope you are aware of the Stokes hypothesis, where the shear stress is defined in this particular way, where you have both the lambda, mu and lambda. Mu is your coefficient of viscosity, and lambda is something that deals with the compressibility effects, where delta is your Kronecker delta. It is defined as, like, it is essentially, it will be 1.
identity matrix.
Yeah, it's an identity matrix. So what the question is essentially asks is it's like from the Stokes hypothesis, if I am saying that the mean value of the principal stress is equal to the thermodynamic pressure. Thermodynamic pressure is this one. So what will be the relation between mu and lambda? This is the basis on which your Navier-Stokes equation will be derived subsequently. So what I'm essentially asking is, using this formula you can construct your tau matrix. In that tau matrix, if you calculate the trace of the matrix, that is essentially the sum of diagonal elements, and then take an average of them, that is essentially tau 11 plus 1 2 plus 1 3, sorry, 2 2 and 3 3. By average by 3, we essentially, what I am saying is this particular average is equal to the thermodynamic pressure itself. If this particular relation has to hold, what would be the relation between mu and lambda?
We have to take
So you essentially have to, using the tensor notation that we've discussed previously, so you have to come up with expressions for each of these terms, tau 1 1, 2 2 and 3 3, and then take an average of them and then equate it to minus p. So if you do that,
PP gets cancelled and
sorry,
PP gets cancelled.
yeah, pp gets cancelled, so then you should be having some relation between mu and lambda. So if I just, I'll write one expression like, so that you can write for 2 2 and 3 3. So for tau 1 1, what you
I
get?
think they use 2/3 of the viscosity, right? I think lambda equal.
So you're saying lambda is essentially 2 times mu by 3.
Yeah.
This is what you have got, right? Okay, we'll
Yes.
see if that is what we get. So I'm just writing expression for one of them. Tau 1 1 is essentially mu times, like I equal to j for tau 1 1, so it's del u del x, and you get another del u del x plus lambda times del dot u. So similarly, when you write for tau 2 2 and tau 3 3, you get the same value for p, and here you get 2 times del v del y, tu mu times del w del z, and for the lambda you will be having the same. So if you just take an average of these quantities, you will get minus p on the left hand side, on the right hand side you will get a minus p plus 2 mu by 3 times, you have del u del x plus del v del y plus del w del z, lambda times del dot u. So this essentially is your del dot u. So the relation you are getting is lambda plus 2 mu by 3 equal to 0. So it's essentially you need to have a minus over here.
Yes.
So we
Yeah.
no problem.
Sorry.
It doesn't matter if it's compressible or incompressible. That's what I am.
Yeah, for a compressible fluid, like this term, second term itself goes to 0. So essentially you don't have a lambda for incompressible
But
flow.
Even this is a 0, right? OU by 2x is 0.
For incompressible flow, this itself is 0. So it will anyway be satisfied.
So that's what. So I think I'm just trying to understand. Like this relation is doesn't matter if the flow is compressible or incompressible. Essentially,
Yeah.
that full part like
Yes.
going away. But that's good. If it is incompressible, as you are saying, lambda it doesn't matter.
Yeah, the term lambda itself will be gone. So that is what you will be left with.
Do you have any large number range that where only we can apply this relation, or like it's applicable for wide range of hot range of flows using this actually accepted Stokes happens.
Like that is a fundamental assumption used in deriving Navier-Stokes equation itself. It is an hypothesis where it is widely valid, but then you have tried the relation you are using for tau itself is for a Newtonian fluid itself. But usually we like the present course only deals with incompressible flows. So essentially you don't have that lambda term. So you'll be dealing with just the Newtonian flow. So now in this question we'll try to do some detailed derivation. So we'll just consider a compressible flow, like we'll include the effect of compressibility here, and then eventually from there we'll try to put del dot u equal to 0 and come up with the values of what the Navier-Stokes would have come, the final relation of Navier-Stokes equation. But before coming to that, the question essentially asks you to derive only for the x component momentum equation for a Newtonian fluid. So essentially what I'm asking you to do is you have rho times du by dt is essentially this should be equal to the sum of all forces acting on your fluid element. So that will essentially give you minus del p del x, plus you have some terms because of the shear stress. Say for suppose we'll ignore the body forces for now, or say the body gravity is along z direction or something. So essentially we don't have that in the x component. So if this is my original equation. So what I'm asking you to do now is you know the relation between tau, like for a Newtonian fluid, tau xx is essentially from, you can use the formula which we have used previously. So this is how you define it. Remove this thermodynamic pressure. So I have already separated it out. So I have written the first expression minus del p del x. So tau xx will essentially be 2 mu del u del x, plus we have seen lambda is essentially del dot u. Similarly, you write expressions for tau yx and tau zx and then come up with the final value of this particular, the RHS value. If you simplify that, what is the expression you would be getting? And then once you get that expression, try to put the values of like while you are applying the derivative, like here del x of tau x, do not assume mu and rho to be constant. Assume them as variables. They can vary within the fluid, they can vary as a function of both space and time. Assume in that particular way and try to expand it. So you might think like though it is a computational course, it might be good to see all these model equations, because eventually you need to have a model before trying to solve it. Maybe like this takes some time, so maybe I will also start deriving it. You can also do it parallelly. Tau yx is essentially your mu times del u del y plus del v del x, minus lambda is essentially minus 2 mu by 3. So if mu is not constant, then you'll be having two terms, one with respect to the derivative of mu and the other one with respect to x. Similarly for the second one. So you see the challenge here when you are dealing with flows where your viscosity and density varies as a function of both space and time, then you need to know the precise functions of the how they vary actually along the space and time. So if you are having a fluid whose viscosity is changing with respect to space, you need to actually know the values beforehand to be able to solve them. How do we actually get that is a different problem. Similarly, if you do for, this is just more of some arithmetic operations which I hope you will be able to do. So applying chain rule, this is what we get, and similarly we have square plus del square v by del x del y, and the second term will be similar to the above expression. This should also be similar. So you have first term with respect to derivative of mu. So I hope you got the hang of it. Now when you take the summation of all these three equations, 1, 2 and 3, so maybe I'll use the tensor notation. If you see the common terms over there, there is an expression for that I would like to highlight. If you see the term over here, there is a del square u by del x square, del square u by del y square, and del square u by del z square. So if I just bring them together, that is your Laplace of u component of velocity, and then you have so many other terms. So this first part is essentially what you see in your Navier-Stokes equation. So if you were to write the complete equation from here, so you would essentially get rho times du dt is your x component of force, that is minus del p del x plus mu times del square u plus some terms, and all these terms are essentially, if you see, most of the terms are either dependent on your del dot u and then various properties, how they change with respect to how mu changes with respect to space and time. So if you take further assumptions of incompressibility where your del dot u goes to 0, and in that particular case all these terms, even this term will go to 0 if you consider it as incompressible flow. Essentially the terms containing whatever is the coefficient of minus 2 mu by 3 will essentially go to 0, and then if you assume constant viscosity, then all the terms in this bracket, whatever comes up after you do the summation, will essentially go to 0, and you will be left with this expression. That is your Navier-Stokes equation. maybe you can try adding all this and then you can simplify, and then you will be able to see that much better. In the interest of time, I will be skipping this detailed derivation. Maybe this is of some concern, it might be helpful. So this is for regarding the energy equation. So when you take the energy equation, how do you think how do we approach the energy equation? For momentum equation, we start with rho du dt, or for each component we just take rho du dt is essentially your summation of all your forces along x direction. So similarly for energy equation, what is it that we start with?
Work done by pressure and heat, discuss forces, energy, rate of change of energy.
So okay, maybe we'll put it more mathematically. So you are saying rate of change of energy. So I'll start with rho dE dt. So this should be equal to
Forces work done by
Heat added to the particle.
okay. Heat. Someone said heat. Someone said work.
Yeah, work done by the fluid and heat added.
So what is it that comes in between, plus or minus?
Plus.
Okay, so this heat added to the system, and this is work done by the system. Okay. So what is the notation you have been following in the thermodynamics? I'm not aware, like if you are from a chemical background you might be using it different, from mechanical they will be using different. So in mechanical what we generally use is if work is done by the system, we consider it to be positive.
Yes.
So if that is the notation we will be following throughout this course. So do you think a plus comes here or a minus?
Yes.
It's a plus term.
It's a plus term. Okay. So if work is done by the system, so I am saying this is a positive quantity. So what is your notation you will be following for heat added? If heat is added to the system, you are considering it positive or negative?
That's positive.
You are considering it to be positive. So let's say suppose you have added some heat to the system, or say consider an adiabatic case where you do not add any heat to the system, but then your work is essentially positive because work is being done by the system. So the work should be done at the expense of its internal energy, right? Its internal energy has to decrease, only then it can do the work. There is no heat transfer. So in that particular scenario, I think you got it right. So if work is being done by the system, it means essentially it has to use its own internal energy to do the work. By the notation you are following, dE by dt will be less than 0 if work is being done by the system. So when your heat added to the system is essentially 0, your LHS is negative, but if you use a plus over here, your RHS will be positive. So the equation is not consistent, right?
So actually I want to just do something here. So it's really confusing when you see system analysis. I have a simple idea to put it.
Yeah,
Correct.
yeah, sure.
So really confusing thermodynamics and mechanical engineering as well. So when you say work done by the system, so I think now I understood. Like so dE by dt is essentially a material body. So it's like it's a fluid particle, and the system is all the system around the particle.
Essentially the fluid particle is your system. I mean the fluid element. It's not a fluid particle. We won't be dealing with one particle. We'll be dealing with some element.
I'm an element.
Yeah.
So you have this. So this is the system for me.
This is my system.
fluid
The
particle.
fluid element is my system.
If when you say work done by the system, what I'm assuming is, because essentially what I want is I want rho dE by dt to increase.
You want
Why?
rho dE
Why?
by dt to increase.
I'm assuming that
Okay.
if rho times or internal energy to increase, the system, this is a fluid particle,
Yes.
and the system, I'm assuming around this fluid part, the other fluid is system, and if it is working on this system, then my dE by dt will increase. And as you said, since there is no heat addition, the work, the energy doesn't come from anywhere. So essentially, the internal energy of the system, not the fluid particle system, should reduce, and that will increase the internal energy of this particle. That
So
is-
okay,
and-
so okay, I got it. So essentially you are considering the surround. Okay, there is some slight confusion, I guess. So for you,
But
the
when you
system
say
is
that-
essentially what is surrounding the particle, right?
So, but when you say system is acting, system is applying forces. So it is applying forces. its internal energy has to reduce because it is essentially transferring energy to out of the, if you assume reverse.
Yeah,
Then
I got your point. So essentially, how we are dealing with essentially is because whatever the fluid element you are considering, on which you are writing all these equations, that is your system. That is the notation that we will be following in deriving all the equations. The surrounding fluid particles will come under surroundings.
Then I think the work done by the system should be less than zero, right?
Or you can define it that way, or if you can still put it as positive and put a minus over here, anything works.
Yeah, that's what. Because essentially, our if work is doing by the system, then its internal energy is reducing.
Yeah, usually the notation is like whatever is your interest is your system. My interest is the fluid element, not the surroundings.
Very clear.
Yeah. So if we come to the previous question where we try to get the power. So what do you think it is? Like we got an expression for power as minus del del xi of p times ui plus
Xi to ij ui.
to ji. So what do you think this is? Is this on the system or by the system?
It's on the system.
So this is on the system because your pressure and shear stresses are acting on the surface and they're trying to change your system. So this is on the system. So this essentially goes into this. And what is the heat added to the system? So maybe I'll just put W for the sake of consistency. So this is the work done rate. So I'm just putting a minus here just to be consistent that work done on the system is essentially negative. So I'm just putting a minus before that to just signify that. And what is the heat added to the system?
It has to be greater than 0.
I mean, it's not like greater than 0, like we assume that heat is being added to the system, we assume some field and then we try to apply something and then we come out with some value. If it turns out to be positive, then it is heat added. If it's negative, then it means it's removed from the system. But okay, that's a different question. The point I was trying to make is how do you get the value of heat added? So basically what I'm trying to ask is, you have some system, you have some Qx, then you will be having, yeah, so that is what I was trying to make. So you have something like this. So essentially the net heat that is added to the system in this particular case will be, if Qx is essentially your heat flux that is moving along x direction.
So it's the divergence of Q. That will be net. Divergence of Q will give us.
Divergence of Q will give net influx or outflux.
So influx of the, if it is positive, it is incoming.
So if it is positive, it is incoming, and if it's negative, it's outgoing. So how do you justify this particular statement? Like how can you say if divergence is positive, it is incoming, or the otherwise, vice versa? How are you justifying that?
Like incompressibility. So you have compressibility. If you have velocities.
So okay, let's replace Q with U. If it equal to 0, then the net flux is 0. That is fine. So if instead of equal to 0, if I say it is positive, so does that mean, what does that mean? If del dot U is positive, what does that mean? More fluid is coming in or going out?
Coming in.
Okay, so if you recollect the previous equation, the original conservation of mass, I think you remember this, material derivative plus rho times del dot U equal to 0, right? This is conservation of mass. So from this particular expression, if you see, if del dot U is positive and for the total equation to be 0, the option you are left with is, if this is positive, this should be negative, right? So what does that mean? Your density is decreasing, which means the fluid is going out or coming in?
It's reverse.
It's reverse. So essentially your divergence gives you the net outflux.
U has to be greater than 0 on the right, so more fluid is moving very faster and is fluid coming with less. So yeah, it's reverse. I said.
Okay. So now coming back to our original question of heat flux. So my objective is to determine the total heat added to the system. So what is del dot Q here? Will it give me net influx or net outflux?
both are depending on the greater than 0 or less than 0. Right?
No, del dot q will always give you some quantity. It always represents one quantity. Whether it is inlet, like del dot q is essentially net outflux. If it is positive, you are saying it as out. If it is negative, you have defined it to be positive, but then you eventually turned out to get a value of negative, which means it is an influx. If you remember, like in your plus 2, you might be solving some of these equations where you have some block on block, and then you'll be having some friction force and all of that. You initially assume some direction for the force, and then you solve the set of equations, and then you come up with some value. If the value is positive, it means whatever you have assumed is correct. If it turns out to be negative, it means it's opposite of that. In a similar way, here del dot q is assumed to be outflux. So
Okay. I understand.
you understood that, right? So the question is now our objective is to get the heat added to the system. So whether del dot q will give me heat added to the system or removed from the system.
Use me get heat removed from this.
So for me to get the heat added to the system, I should put a minus before it, right?
Minus.
So this is your heat added to the system. The problem here is if you just use this equation, we do not know this qx, qy and qz. So we need to have a closure form of it, and that's where your Fourier equation comes into picture, where your q is related to your temperature field. Okay, now maybe I should ask again. So do you think minus comes here or not? Maybe there is some confusion regarding the signs.
Well,
Minus,
P.
Sorry?
minus sign, I think.
So there should be a minus.
Yes.
Okay, there is some.
Like say the temperature is changing from
Because the temperature is it fluctuates from high to low, right?
Heat flows from high to low.
Yeah.
minus of period.
So essentially have this as minus.
Yeah.
So what is my total heat added now is essentially your minus del dot.
Minus of K, so minus goes and efficient get positive.
Yeah, if your thermal conductivity is assumed to be a constant, then you essentially get K del square T. So before going to that, the energy which you have defined here, E, is your total.
Prasad,
Yeah.
I need a small clarification.
Yeah.
See, if the flow is coming more, inside a system, so outflow will be less. So how could we deal in that situation? In fact, what would be the convective terms if it is likely to be?
Sorry, I didn't get your question. So if the inflow is higher than the outflow,
Yes.
so what you want?
What would be the sign indication for the equations?
No, the equations will remain the same.
Okay.
The notation is such that when you after solving the equation, you will be finally getting some terms, right? You have assumed everything to be in particular way, like say suppose if you just take the continuity equation itself, this is your continuity equation. Our assumption is del dot u is essentially positive, which means your net outflow is higher. If this turns out to be positive, this turns out to be negative. If it is other way around, like if your del dot u is negative, then this term will be positive. So like the equation ensures that the entire thing remains the same.
Okay.
But initially we need to have some assumption, right? That is what I was trying to emphasize on. Del dot q essentially signifies the net outflux, or del dot any vector will, or you can, if you are aware of, you should be coming across Gauss divergence theorem, where you have across any closed surface, if you just take an outflux, it will be equal to your volume integral. So if you just even take from this expression, what I am saying is f dot ds will be essentially positive if your f and if f bar or your vector is along the direction pointing the outward normal of the surface, right? That is when
Yes.
this left hand side will be positive. So del dot f will be positive only when f bar is directed outwards. So you can understand even from there.
I understand.
Yeah. So let's come back to this question. So we started out saying we need to find an expression for dE dt, but what is E here? E is your total energy, or it's essentially specific energy, but your total energy essentially contains several other components. One is your internal energy, and for now we are and then your kinetic energy. So I'm just writing ui, essentially it means u square plus v square plus w square. This small a is essentially your internal energy, and then for now we'll neglect the potential energy and all of that. So this is your E. So when I ask you to find dE dt, maybe you can try this. If I just do rho times dE dt, what do you think it gives me? Rho times di dt plus, you can expand this as rho ui times dui dt. So if you observe this, this can be written as rho dui dt times ui. Like this is essentially your velocity term, and this is your force term. So your total energy, you are again coming in terms of either it has to be to the internal energy, or it has to be some power or work term kind of stuff. The question is essentially asking about to relate it with respect to the enthalpy. So how do you define enthalpy? I mean, I used an expression there, like I was asking you to derive, say suppose I derive a new quantity h, I define it as h equal to E plus P by rho. I defined it this particular way, and then okay, maybe rho and P are looking similar. I just use P by rho. So I am asking you to derive what is the expression for rho times dH by dt.
My network is news.
Sorry, I didn't get you.
My network is giving trouble, but anyway. No. Continue.
Okay. So if you start from the same expression h equal to E plus P by rho, or maybe you can do it parallelly. You get rho times h equals rho times E plus P. Now if I apply the material derivative on both sides, you will essentially end up with rho times dH dt or maybe we will simplify the question. As per the question, it asks about for incompressible flow. I guess, yeah, it's an unsteady and incompressible flow. So for an incompressible flow, we have seen previously that this particular term goes to 0. Essentially your rho is constant. So when you are applying your material derivative, you can just take it out. So rho times dE dt plus dP dt. So rho times dH dt gives you rho times dE dt, where dE dt we already have an expression. dE dt is essentially this particular term over here. So we just substitute that back. So we get rho times di dt plus rho ui dui dt plus dp dt. It's a material derivative, we can kind of expand it. We get dou p dou t plus ui del p del xi. So essentially have del p del t, or maybe we should expand this particular term. So what you have ui times rho times dui dt, where rho times dui dt is again you can use the momentum equation. So you will essentially get minus del p del xi, or maybe I will substitute that directly. So you get rho times di dt plus ui times, you have rho times del u del t is essentially minus del p del xi plus del xi if body forces are neglected, plus del P del T plus ui. Can one of you mute yourself? There is some background noise. Yeah, thank you. So we have del P del T plus ui times del P del xi. So this particular term goes off. So this gives you rho dh dt is essentially rho times di dt plus del P del T plus ui times ji by del xi. And that is what is asked in the question. So we have del P del T and then rho di dt and ui times del tau ji by del xi. Say for suppose you have a simplified case where you have a steady flow, this particular term goes to 0. Okay, maybe let me put this question this way. So for a steady flow, do you think the LHS goes to 0? If I say it is a steady flow, will the material derivative be 0?
No, it should not, because it has convective term.
It has convective to some, so it can or may not be 0 depending on how it varies spatially. Okay. Now we will go to the energy equation. So if you have gone through the lecture videos, you might have seen this energy equation where the internal energy is related, but we won't be dealing with internal energy as such. We will assume it follows some law as I equal to some specific heat times temperature, and eventually our entire equation will be in terms of temperature field and velocity field. So if you see this expression, you have rho di dt will give you energy term. This is your pressure times, so this is essentially your work done part, and this is your heat part, and then there is some additional term called phi. This essentially comes when you consider flow to be viscous. So this is your viscous dissipation term. So I would like, maybe I'll wait for some time so you can try to derive this expression for phi. It will be in terms of velocity fields and your viscosity, coefficient of viscosity. Just to ask, you have two set of parallel plates, and then a fluid is flowing between these two plates. Say suppose they are infinitely parallel, and then if I am using the previous expression, there I have a quantity called K. So it essentially is rho times di dt this essentially is your divergence, and if the flow is incompressible, this term goes off, minus so this is your heat. Is this heat addition or removal? Maybe I should ask this at this point of time. So essentially what we are trying to say is the total internal energy change will have two components to it, either because of internal and by the way, what do you think this K value is? Is this of the fluid, thermal conductivity of the fluid, right? So what is this term signifying? If I am saying K del T del X, what is that term signifying? So does it mean the heat transfer into the fluid or out of the fluid? Say KCA is this one,
Both,
KSP is this.
it transfers both. It transfers fluid to material and material to fluid. It's the conduction, right?
So, no, what I was trying to ask is, if I consider a fluid, like this entire differential equation is for a fluid element, right? The equation is derived for a fluid element. So for the fluid element, the internal energy change should be equal to some heat term and some viscous dissipation term. Your internal energy can increase either because of these two. So this term is essentially should be like a heat addition term or removal term. Like which
So
of
that
these
full term, including the negative, is heat added to the
system?
fluid part.
Yeah. Otherwise, your internal energy will not increase.
Yes. Essentially, we want internal energy to increase, and I guessed it. I mean, we have derived it already.
So I'm just not rederiving it. So you
No,
got the
because
crux of it, right? So you just have to be conversant with it. So what do you think the second term will be? This viscous term. Will it increase or decrease? Like I put a plus over it. So ideally, what do you expect for the viscous term to be?
Should reduce the
Decrease. Should decrease, I think. Should decrease the viscous.
So this term can be either positive or negative. Like I put a plus sign here, but that is of no use. Forget about the plus sign for now.
Negative. It should be negative.
Okay, so it should be negative. Okay. Anyone who says positive? Okay, maybe I just want to hear what is the justification for your assumption that it will be negative.
Probably see if internal energy increase, for the fluid, in fact. So what would be the viscous? Obviously, viscous will reduce, I think, right?
Okay, let me put the question in a different way. So say suppose just consider the same case between two parallel plates. If fluid is flowing, now because of viscosity, what happens is the fluid velocity gets converted into thermal energy, right?
Yes.
So the fluid velocity is reducing. So essentially, your viscous is increasing your internal energy. It is drawing energy from the fluid, kinetic energy, and then dissipating it as thermal energy.
Yes.
So your viscous term will increase your internal energy. So it should be positive, right? It will decrease the velocity, but it will try to increase the mean temperature of the fluid.
Yeah. So see that you take the parcel and it is moving in this viscous.
Sorry, I didn't get it. We take a?
So we take a fluid parcel.
Okay.
And we're trying to address the rate of increase or whatever rate of change of internal energy of such fluid parcel.
Okay.
And say that you take some different examples, and you take a block, some solid block, is sliding or it is moving on a frictional flow.
Yeah.
Okay. Say that we are trying to find the energy of such
of the block.
Of the solid block, not fluid block.
Yeah, of the solid block.
So the forces acting on such block is the external force applying. It will increase the energy of this block. And then
that's why your block gets heated up.
And you have this frictional force, which is viscous.
Yes.
Okay, that will essentially reduce the energy of this block, but it doesn't reduce because energy is always constant. Okay. So because of this frictional force, the temperature has to increase, and we should have an additional equation here for this energy equation, which actually, we should deal with the rate of change of temperature of the block. Then that change, that temperature equation, there we will have this change in temperature, and the temperature equation is reflected in the second term, and that way the energy will always be constant.
So what do you think the expression for I will be? So I is essentially C times T, some specific heat.
Okay.
So the left hand side essentially tells you how your temperature changes with respect to time. So that is expression you are stating, right? So you should have some temperature relation. Your temperature change with respect to time, that is your LHS. On the RHS, you will be having heat addition terms and this viscous dissipation, that is essentially the effects of friction force. The only difference between a solid and a fluid is inside a fluid within the
Pressure forces.
sorry.
You have additional pressure forces in fluid, but you solid block you don't have such. That's the only difference I'm seeing. Solid and fluid.
Okay. That's fine. The one I was trying to emphasize on is essentially because, say, if you just consider this parallel plates, flow between two parallel plates. Okay, it might be parabola, just assume it to be parabola or something. So essentially each layer when moving across other layer will lose energy, right? If my fluid element is considered at this scale, then internally there will be a lot of these viscous forces. There will be velocity gradients. Because of the velocity gradients, the energy will be lost and it will be converted into thermal energy. You might be seeing, like, if you are aware of turbulent modeling, you might be aware of energy cascading. If not, okay, let us forget that.
No, in fact, Prasad, so what if it is in compressible, then internal energy and thermal energy come into the picture, right?
Internal
If
and
it
thermal
is,
energy will always be
yeah,
there, but why does it have to be compressible?
if it is the flow will be say if the flow, if the flow is compressible, then internal energy come into the picture. In fact,
If it is
otherwise, if it
incompressible,
is, yeah, no, see, the flow, if the flow is compressible, so the internal energy will be changed, right? So obviously we can
if it
see in
is,
textural aerodynamics, right?
yeah,
If the flow will be the supersonic,
then
obviously
eventually your
internal energy
temperature and everything will change.
everything is okay. Yeah.
That is fine.
See here, yeah, it is an incompressible. See, incompressible means there is no any fluctuations in density, right?
Yes.
Density. So how could the internal energy come into the picture?
Yeah, if you consider a viscous fluid, just consider this example between two parallel plates where you just have the viscous forces are dominant, then your fluid velocity should be, energy is getting lost, right? Your fluid will be decelerating, right? There is a velocity gradient.
Yes.
Initially you have the uniform flow, but then once after it gets into the parallel plate, there is a velocity profile, which means the energy velocity which was there previously is not present now. Where do you think the energy lost is going to?
Yeah.
It has to eventually increase the internal energy of the fluid, and that's how your temperature will be changing. Then you will have a temperature gradient as well inside.
Okay. Yeah.
So if you try to derive the expression for this phi,
Actually, I'm not convinced with that one, but
okay,
I have to check it once. I'm not
yeah,
sure about it because the complete velocity profile will be developed after the hydrodynamic length. In fact, right?
yes,
I think, and it is loss of due to loss of internal energy or maybe
due to
check it.
loss of its velocity, it gets converted into this one. Essentially, the you see, when a fluid just touches a solid, because of the no slip condition, previously there has used to be some velocity which is now getting converted to zero, so some energy has to be lost.
Yeah.
So if I tell you that I have an isothermal plate, like depending on your boundary conditions, if I say both the top and bottom plates are isothermal, or maybe I'll just put an adiabatic condition. Isothermal is difficult. Adiabatic you can easily understand. If I have both the top and bottom plates as adiabatic, then no energy can be transferred to the plate. So the only option left is the dissipated energy should be absorbed by the fluid.
Okay. Okay.
If you have an isothermal case, there are solutions for that. You can Google later. So you will find solutions for isothermal case as well. How the flow develops and how your temperature profiles will be there.
Okay.
And that becomes more and more significant when you have high speed flows. That is the effect of compressibility you were saying, right? When you have high speed flows, those gradients will be much larger and the effects will be significant. But just to know whether it is significant or not, you need to first estimate this term, right? Phi. Phi is your viscous component. I am just saying phi, but what terms are there in the phi? How do you derive that? From whatever has been discussed in the video lectures. I think it's been
We can
discussed.
derive by there are terms. We can derive by some shear stress
So
strains.
yeah, so what is the term that you will get for phi? Like, have you tried solving it now?
No.
Okay. So maybe I'll just give you some hints to start with. We need to close by 7. If it permits, we'll try to close it by then.
This viscous term is have discussed this, right? From the d by dx I times tau I j u g, right? That's the term
So
in
you're saying mu, sorry, can you repeat it again?
dou by dou x I
Mhm.
times tau j I u g. This is the term, the energy term due to shear stress. That's what discussed recently.
This is due to viscous, and this comes in your rho times dE dt plus so and so. So like you have pressure gradient in other terms as well, like static pressure gradient. But then you have to relate this with your internal energy. Like E is your total energy that contains both the kinetic energy as well as your internal energy. So like if you remember,
Yeah.
so E essentially has these two components. So you need to split this up again. So here you will essentially come up with again rho times di dt, plus you will be having one more term, rho ui dy dt, where again here rho times dy dt will again further have your shear stress terms. So like this will again come up to be ui times del p del xi plus ui times del xi tau ji, and this comes out to be your del xi. So if you expand these expressions, like if you take these expressions to your RHS, then you will eventually come to be rho dou I dou T. You will have some heat term, then you will have some pressure term, like static pressure term, and there will be some shear stress term. Like you will have some pressure term, some heat term, and some shear term. And this shear term is what that contributes to your viscous stress. So I will be just focusing on the shear term. So if you see, we'll be having del minus ui times so this gives you tau ji into del ui okay, there is some mistake here. It's uj it's uj. Maybe I'll just try deriving only for the 2D case. You can later expand for a 3D case. So for a 2D case, you have this expression comes down to del x. So you can have tau xx you can also have tau yy. Similarly, on the right hand side, you will have ux del x of tau xx minus ux del x tau ix uy plus del y tau xy ux. You can have uy del y tau xy minus uy del y tau yy. If you substitute back the original equations where 2xx will give you 2 mu del u del x. So we are just considering only the incompressible flow for now. 2yx or 2xy, both of them will eventually give you u del y. If you substitute these equations in one, what you will get is something like mu times del u del x square plus 2 times del v del y square plus del u del y plus del v del x whole square. It's like this is for just a 2D flow. If you expand it for a 3D flow, I mean for all the 3 dimensions, your phi will turn out to be something like del u del x square and all the cross terms. Cross terms are essentially del u del y plus so this is expression you will get if you do it for the full 3D flow. Maybe I think we have some 15 minutes. It's like, will you be able to go through the math, or do you want me to just go through the math as well?
You try this. Can you share the slides, like whatever you have done somewhere? Is it possible?
Yeah, sure. You will find a link in the NPTEL course itself, like where you see your week 0, week 1 lectures. At the bottom, you will find one problem solving session. Like it will be updated. I think it's not updated as of now. In that session, you will be given one Google Drive link where you can access all of this. Even the session is recorded and it will be uploaded on YouTube.
And slides are much better to
Yeah, sure. Yeah.
So I have some general questions about the course. I think we have some time.
Yeah, sure.
I'm just wondering, do we do any coding in this course? Like coding as in not explicit coding, at least.
Okay. By general questions, you mean that? Okay, I'm not that aware of. I'm actually not not associated with the instructor, so I'm as a separate team from that. So I don't think there will be a coding session in that, but I'm not sure about that. Maybe I'll get back to you on that after speaking with the instructor. Essentially, the main objective for these sessions is to help you in solving your assignments.
Yeah, no, it's right, because the assignments has this how to mesh all the questions.
Okay.
Do you come to the next week or somebody else?
No, I'll be there for all the sessions. So every Saturday, like 5 to 7, we'll be having this, and I'll be the only I will be the one for all the sessions.
So if you can stop presenting so that I can ask the questions, that's better, right?
Yeah, okay, fine. If everyone is fine with that, I'll just a second.
I hope they are.
Yeah, 1 second.
Because
yeah.
Not stop. Stop recording.
Oh no. Okay, it's supposed to be recorded. Okay, you have some questions that are not related to this one.
Of course, regarding the course.
So then you can.
My target is say that you have block of code, and I want to study. I take a sheet ball, they drop it in the school. And the way to do this is using some immersed ground methods. There are different methods.
Yeah, that is essentially not discussed.
So in finite volume, you don't have. I don't think how to do free surfaces in finite volumes. I'm not. I don't know.
Okay, that is essentially not a part of this course.
it is not.
Huh.
Okay. My question is,
Yeah.
so at least not even think that. Say I take a block and I want to code this by myself.
Okay.
Say I do fishing and
Hmm.
solve the cells, how to have data structures, not even data structures.
Okay.
I'm just expecting maybe 12 weeks. I think it's 10 weeks course. At the end of 10 weeks, will I be in a state at least to use some existing software, not commercial, something like
Huh.
OpenFOAM or
Okay.
SU2 or
So if you
will
want to
you
write
think that?
your own codes, or you want to like if you want to write your own codes, I can plan sessions accordingly. Like I can have some coding sessions also. I'll speak with
Yeah,
instructor and we can have some coding sessions.
that would be good. Yeah.
But the language should be of your choice. I mean, I can't tell in all languages. I'm like used to C++. So if you're used to some like the entire structure will be similar. I can explain you the basic structure. So
Yeah, I will be.
yeah,
No,
that is fine.
code is greatly useful. I'm happy if you can do that.
Yeah, sure.
And
That
I'm
I'll speak
others
with the
are
instructor. I'll speak with the instructor, and if he's fine with it, we can have actually
because
the session is for 2 hours. We can split into 1 hour each. Where first half an hour we can discuss on the assignment problems. The second half an hour we can take one exam problem and code for it. Like I can show you some codes.
so like I maybe some target for 10 weeks. I'm just telling you now. Maybe there could
Okay.
be a simple driven cavity problem, which should be enough. Like at least from ground up. Like take
Yeah, yeah.
scratch. You define your mesh. You define cells. You define how you're finding the fluxes. No, and if I
Okay.
think that would be good target to reach. Right? I don't know. So you should tell me how difficult it is to get finite volume methods to achieve that level.
It's like if you want to write the meshing also on your own, then we might have to go to some software. Like it
Mesh
will
is
become
not
difficult.
just able to solve. I think existing mesh, like at least regarding finite volume. So like if you ask me, my target is you take any paper in 2022 or 2023, and if it is related to finite volume methods,
So you should be
let's
able to
that's
reproduce it.
able to reproduce it, understand it. Okay, this is what he's doing. Maybe he's adding some electromagnetic force to it, and if you're
Okay.
trying to see how the flow is happening, so at least to understand whether I can use the existing commercial or not commercial, any
No, no.
existing open source
Commercial
software.
software is okay. We will not be taking up any commercial software. Maybe we can take up the first part you were mentioning. We can write our own
So
codes, not into any
I don't know.
commercial software, but our own
If
codes, but for a simpler problems.
exactly. So we don't want commercial. I don't want commercial software. I want to be. I want to understand how the back end of it.
Yeah,
So that I can
yeah,
easily
yeah. That is
understand
fine.
existing open
Yeah,
source
yeah.
softwares and modify it and use it for my research or according to have fun or something.
Okay, that is
That's
fine. That I will speak with him, and we can have some questions. I mean, coding questions. Yeah, you can.
Nagaraj.
Yeah, you have someone raised a hand. Yeah.
Yeah.
Sorry.
Prasad, oh, I think I hope you will be the person for the all remaining sessions
Yes.
without clarification, right? And, may I know, do you have an idea about some algorithms like simple, simplex, coupled?
I haven't used them, but I have the basic as far as the course is allowed.
Because in Answers Fluent, there are some algorithms to solve some
Simple will
equations.
be discussed as part of the course.
Okay. Simplex.
Simplex, I think only introduction, like the idea will be presented for simplex, simpler, and all of them. Simplex, simplex, simpler, all of that idea will be will be given. That's what I have in the course as part of the course. But implementing them is actually not. I mean, it's quite involved
Okay.
by yourself.
And yeah. And have you come across Answers Fluent, Prasad?
Yeah, I haven't used, but I use Comsol, but yeah, it should be similar.
No, actually, I have a doubt regarding the woman cut streets. That.
Okay, okay, okay. I'm not aware of that. I mean, I'm not used to that.
Okay, okay. It's okay. It's okay. Then
Yeah,
if you use that one, then I will proceed my doubt.
yeah, yeah. No, no, I haven't used.
I think he only wants us to ask him
Related to
questions
the
related
course, yeah.
to course and anything
Anything
else.
outside of that we can discuss after the
So
session. Like you have
I think
one.
you didn't
Actually,
say
it's related to the course, but of course, it's a part of the course. But I don't know whether it is included in the course or not.
Okay,
Right?
basically what is included is the method. It's essentially applying FVM to some of these equations. We discuss on some diffusion. convection diffusion, like pure diffusion, and then discussion on convective diffusion equations, and then we will discuss how simple and all these things can be applied using finite volume method. The focus is on method itself, not on the problem.
Turbulence equations, turbulence models, K omega,
No, no, no,
K
no, no,
epsilon,
no, no,
transport
no,
equations.
no.
These
Essentially, I think
topics, these topics are not included in the course.
Turbulence equation, no, K epsilon model is not included.
Okay.
I think what this course essentially addresses is, so you have these partial differential equations,
Yes.
whatever it is derived now. You take this. There are several different kinds of numerical techniques,
To
mesh
solve
less,
them.
mesh
Yes.
element finite difference, all the stuff. We are only addressing how to solve these specific equations using finite volume technique.
Exactly.
Like how to you like if you go
Given
to
the model, how do you solve it using finite volume method? That's it.
Exactly. So you have this Poisson equation, which is kind of viscous equation, all these kind of equations. So how would you use them and use FEM to solve them
Solve it.
numerically on it? So that's why I asked, can we do it like can I add computer coding? That's it. Okay.
Any coding sessions are included in this
It's like
course?
as of now, it's not there, but I'll speak to the instructor. Like if more of you are instructor, then maybe we can have a session. But we cannot teach the coding, but the basic structure I can explain all of that, like how you set up and all of that.
Okay.
I think that would, you just, why don't you just take a, not a poll exactly, because if people don't know coding, it will be difficult for them to I think they'll just leave the call. Like it will be, I don't
Yeah,
know.
that's exactly what I was thinking.
Uh, So you
So
can make it very minimal, or maybe you can have one more session. Maybe if you have time, maybe like half an hour, this strong, or 1 hour. If you can do it, that would be great. Because you just see who is the audience, and if there are many audience, you can arrange. Else, I don't want, but I will definitely attend. I'm more interested in that part.
actually there are 700 students enrolled, and I'm not sure about that.
Okay. So you didn't introduce yourself, by the way. I think it's part of course. You introduce
Yeah,
yourself. I guess.
yeah. In the starting, so just to say, like I'm currently a PhD scholar in IIT Madras. So, as part of this, this is as part of our tier 2T, we are considering this. Essentially, the objective is to give the problem solving sessions for you. If you have any doubts in the lectures or anything in the previous weeks, we can discuss on all that. And any other queries other than the questions I have discussed, you can post in the discussion forum. It will be addressed by the instructor and his TAs.
Okay.
Great.
If you don't have any queries, I think we are well within time, and maybe you have
Please, so
6
yeah,
minutes.
please ask Professor. What is his name? Professor to regarding this coding thing.
Yeah, yeah, sure. There are some codes on, like there are some example codes in Fortran that he uploaded on NPTEL. I think you don't have access route right now, but you will be getting access to that. Those are for the cases you have, it's on a porous solid and all of that. But they are not specific questions, they are just to explain you the method, that's it. That's what I was trying to
Porous
emphasize
solid
on.
is too advanced model, no? I
No,
think
no,
this
the
whatever
model
you
is
are-
already given. The model will, the differential equation will already be given to you in the question, and then you just solve it using FVM. That's it.
And Mr. Dinesh, if you want to do the coding, no problem. So I can give some you know codings on problems, no problem. Because I know MATLAB and Python, and I have solved some numerical problems with MATLAB and Python. There are very simple problems, so I can share you, no problem, if you want.
Yeah, maybe you can make a thread on the forum and share it there.
Yeah,
Yeah, you can share this material in the discussion forum so that
yeah, I can
whoever is
share.
interested, yeah, whoever is interested can take it from there.
I can share because I am, presently, I'm working as a technical support engineer in skilling on CFD domain.
Okay.
I think you might have known that CFD, sorry, skilling,
Yeah,
leading edge tech company.
yeah.
Yeah, right. So I'm working in CFD domain. No problem. So I can share the, some coding problems, MATLAB and Python. No problem. I can share the some documents and materials if you want.
So, Durga, I just want to be it. I don't know. Just you, if you're planning it, just make sure that you know how the structure works. Right? Don't go like too much. Maybe from how to basics. I think if you research, which year are you in right now?
I'm in my second year right now, and I've taken this course previously. Like I've taken the course offline, so we were having coding assignments as such, but since it is an online thing, we don't have all of that. But in the offline course, we were supposed to code and we have to submit and all of that.
Yeah, so I want, if you are doing computation, if you're not coding, it's no more computation. So it's like
That's fine. Maybe I can share I'll speak to the instructor and I'll share the assignments we had during the offline sessions. Like we were having some numerical assignments that we need to solve. I can share those assignments. Like I'll ask his permission and share those assignments. You can.
So are those numerical assignments are from ground up, as in, like from basic FEM, who doesn't know how to do FEM?
Yeah. You need to discretize your own equations and you need to develop your own code. It doesn't focus on meshing and all of that. It doesn't require extensive meshing. It's just a normal rectangular mesh and all of that. Only
you have vertices, cells, and faces. You now write the FEM solver for this.
You don't even have that much. Your focus is only on the solver.
Okay.
It's even simplified. If you want faces and cells, that comes up as you go in the course. But in the initial stages, it's just the normal 1D equations that you will be solving.
Okay, and I have a small doubt.
Yeah.
And it's my last doubt. And Durga Prasad, do you know the history of the CFD in fact?
History in the sense?
When it is implemented and when it is started.
Okay, sorry, I am not aware of that.
Started background history.
No.
Okay, right. Because history in the sense that is also very interesting. When it is started and
how the different methods evolved and all of that, right?
Yes. By the time they invented how the methods are evolved, what was the experience they faced, to be a part of the CFT development.
Yeah.
So, and so do we have these sessions every week or every couple of months?
No, every week.
Okay. So why don't you just, if it's possible, you just ask your is he your supervisor or you just here?
I mean, I'm not actually connected to him, so this is through NPTL. I can contact him anyway.
So just if you can upload first assignment now, the coding assignment, then it will be helpful.
The first coding assignment, I think, okay, week 2 lectures are already uploaded, so maybe you should be able to solve the first assignment.
Just talk to him once and maybe.
Yeah, if he's okay with it, then I can share with it. Or you can also post the question in the discussion forum. He will be seeing that directly.
Yes, but I think through you, it might be much
better. You post in the discussion forum as well. You post in the discussion forum as well. I'll also speak to him personally.
Great. That's all the questions I have. Thanks. The really great derivations. Very helpful.
Yeah, if everyone is fine with it, then I think it's already time we can conclude this one. It's already close to 7. Yeah.
Okay. Thank you, Prasad. Thank you very much. It was very nice to meet you. Very great to be a part of this. Thank you very much.
Thank you all. We'll meet the next week at the same time.
Okay. Thank you, sir.
Thank you, Prasad.
Thank you all.